dear viewers, I am Dr. P.N. Agarwal, professor in the Department of Mathematics, IIT Roorkee. In my lecture, I am going to discuss the various methods of obtaining a general solution of ordinary differential equation of first order and first degree. An ordinary differential equation of first order and first degree can be solved by standard methods if it belongs to one of the following categories, or can be reduced to any one of them. First, equations in which variables are separable. Second, homogeneous equations. Third, exact equations. Fourth is linear equations. All other differential equations of first order and first degree which do not belong to any one of those categories can be solved using numerical methods, which give us an approximate solution of the given differential equation. We shall talk about approximate methods which give us solutions of those differential equations later on. First, we shall discuss those differential equations which can be solved analytically. So, we begin with equations in which variables are separable. Equations reducible to separable form. Let us begin with a ordinary differential equation of first order and first degree. It can be expressed as Mdx+Ndy equal to 0, where m and n are functions of x and y. Now, if we are able to express it in the form gy dy equal to fx dx, where gy is a function of y only and fx is a function of x only, and fx and gy are continuous functions, then we say that the given differential equation belongs to the category of those differential equations where variables are separable. General solution of such a differential equation can then be obtained very easily. We just have to integrate both sides of the given differential equation, and we have integral gy dy equal to integral fx dx plus c, where c is an arbitrary constant of integration. Since f and g are continuous functions, they are integrable. So, the integral of f and integral of g exists, and we obtain the general solution of the given ordinary differential equation. This method is known as the method of separation of variables. Let us consider an example of a first order ordinary differential equation of first degree which belongs to this category of variable separable form. Let us take dy by dx equal to e to the power x minus y plus x square into e to the power minus y. Now, this differential equation can be written as e to the power y dy equal to e to the power x plus x square into dx. When you multiply the given differential equation by e to the power y and then by dx, we arrive at this equation, and we can note that on the left side we have a function of y only, while on the right side we have a function of x only, and therefore, when we integrate both sides of this differential equation, we have integral e to the power y dy equal to integral of e to the power x plus x square into dx plus c, or we will have e to the power y equal to e to the power x plus x cube over 3 plus c, where c is an arbitrary constant. Let us take up another problem, which is y minus x into dy by dx equal to 2 times y square plus dy by dx. Now, this equation can be rewritten as y into 1 minus 2y minus x plus 2 into dy by dx equal to 0, or we may write it as dx over x plus 2 minus dy over y into 1 minus 2y equal to 0. Now, you can see that the variables x and y have again been separated. First term is a function of x only, while the second term is a function of y only, and so this equation is again belongs to the case of differential equations where the variables are separable. We integrate both sides and get integral dx over x plus 2 minus integral of 1 over y plus 2 over 1 minus 2y dy equal to c. Here we have broken the term 1 over y into 1 minus 2y into partial fractions. The partial fractions are 1 over y plus 2 over 1 minus 2y. Now, after integration we get log of x plus 2 minus log y plus log 1 minus 2y equal to log c dash, where we define log c dash equal to c. This will give us x plus 2 into 1 minus 2y equal to c dash y, which is then the general solution of the given differential equation. Now, let us consider the initial value problem dy over dx equal to 4x plus y plus 1 whole square, where y0 equal to 1. An initial value problem is one where the value of the dependent variable y is given at an initial value of x, that is x equal to 0. In the case of this differential equation, we substitute 4x plus y plus 1 equal to t in order to bring it to the variable separable form, because then dy by dx will be equal to dt by dx minus 4, and so we will be getting the given equation in the form dt by dx minus 4 equal to t square, or dt by 4 plus t square equal to dx. You can see now the variables x and t have been separated. On the left hand side we have a function of t only, while on the right hand side we have a function of x. So, after integrating both sides we get half of tan inverse t by 2 equal to x plus c, which is equal to half tan inverse half 4x plus y plus 1 equal to x plus c. Now, when we make use of the initial condition y0 equal to 1, we get c equal to pi by 8, and thus the solution is 4x plus y plus 1 equal to 2 tan 2x plus pi by 4. Let us now take up another case of differential equations, ordinary differential equations of first order and first degree, that is homogeneous equations. If a first order ordinary differential equation of first degree is of the form dy by dx equal to f of y over x, where f is any given function of y over x, we shall call such a differential equation as a homogeneous equation. In order to solve such a differential equation, we put y equal to v into x. Then dy by dx will be equal to v plus x dv by dx, and when we substitute it in the equation 1, we shall have v plus x dv by dx equal to fv, or we can separate the variables x and b and get dv over fv minus b equal to dx over x. Now, we can integrate both sides of this differential equation and then replace vy y over x to obtain the general solution of the given differential equation. Let us take an example of a differential equation belonging to this type. Let us consider 1 plus 2 times e to the power x over y dx plus 2 times e to the power x over y into 1 minus x over y dy equal to 0. You can see here that this differential equation may be written as dy by dx equal to minus 1 plus 2 times e to the power x over y divided by 2 times e to the power x over y into 1 minus x over y. The right hand side of this equation is a function of y over x. So, let us put y equal to vx. Then we shall have v plus x dv by dx equal to minus 1 plus 2 times e to the power 1 over v divided by 2 times e to the power 1 over b into 1 minus 1 over v. We can simplify this equation and get x into dv by dx equal to minus 1 plus 2 times e to the power 1 over v over 2 times e to the power 1 over b minus into 1 minus 1 over b minus v, which will give us, after simplification, minus 1 minus 2 e to the power 1 over b minus 2 times v into e to the power 1 over b plus 2 times e to the power 1 over b divided by 2 times e to the power 1 over b into 1 minus 1 over b. Now, we can bring the variables v on one side and the variable x on the other side and then integrate both sides. So, we shall have integral of 2 e to the power 1 over b into 1 minus 1 over b dv divided by 2b into e to the power 1 over b plus 1 equal to minus integral of dx over x plus c. Now, the denominator 2b e to the power 1 over b plus 1 when we put equal to t, we note that we get the derivative as 2 times e to the power 1 over b minus 1 over b into e to the power 1 over b into dv equal to dt, and so the equation becomes integral dt by t equal to minus log x plus c. The integration gives us log t equal to minus log x plus c, or we may say log of 2b into e to the power 1 over b plus 1 equal to minus log x plus c, which will further give x into 2b e to the power 1 over b plus 1 equal to e to the power c. E to the power c can be written as a new arbitrary constant c dash, and we shall then have x plus 2y e to the power x over y equal to c dash when we put the value of v equal to y over x. So, this is the general solution of the given ordinary differential equation. Now, let us consider the case of the differential equation x dy minus by dx equal to under root x square plus y square dx. This equation may be written as dy by dx equal to y over x plus under root 1 plus y square over x square. So, again we see that this differential equation is dy by dx equal to a function of y over x, and hence this differential equation is a homogeneous differential equation. Now, so we will put y equal to ux here, and that will give us u plus x du by dx equal to u plus under root 1 plus u square. We can separate the variables u and x and get du by under root 1 plus u square equal to dx by x. When we integrate both sides, we get log of u plus under root 1 plus u square equal to log x plus the constant of integration we take here as log c. So, this will give us u plus under root 1 plus u square equal to cx. Let us put the value of u, and we get y over x plus under root 1 plus y square over x square equal to cx, which then gives us the required solution as y plus under root x square plus y square equal to cx square. Now, we consider the case of non-homogeneous equations which are reducible to homogeneous form. The differential equations of the form dy by dx equal to ax plus by plus c over a dash x plus b dash y plus c dash can be solved as follows. First, we take up the case where a over a dash is not equal to b over b dash. So, then we will put x equal to capital X plus h and y equal to capital Y plus k, where h and k are some constants, and this substitution will give us dy by dx equal to ax plus by plus ah plus bk plus c over a dash x plus b dash y plus a dash h plus b dash k plus c dash. Now, we will choose the constants h and k in such a way that ah plus bk plus c equal to 0 and a dash h plus b dash k plus c dash equal to 0. If we do this, then the differential equation will reduce to homogeneous form. The values of h and k can be obtained from the two linear equations involving h and k as vc dash minus b dash c over ab dash minus ba dash and k equal to ca dash minus c dash a over ab dash minus ba dash. Now, since we have assumed that a over a dash is not equal to b over b dash, ab dash minus ba dash is not equal to 0, and therefore, h and k exist. The equation 3 now becomes dy by dx equal to ax plus by over a dash x plus b dash y, which is a homogeneous equation in the variables capital X and capital Y, and can then be solved by putting capital Y equal to v into capital X. Let us take an example of a differential equation of this category. Suppose we consider the differential equation as 2x plus y minus 3 into dy minus x plus 2y minus 3 dx equal to 0. We can write the given differential equation as dy by dx equal to x plus 2y minus 3 over 2x plus y minus 3. And let us note that here a over a dash is half while b over b dash is 2. So, a over a dash is not equal to b over b dash, and therefore, we can put small x equal to capital X plus h and small y equal to capital Y plus k to reduce it to homogeneous form. These substitutions will give us dy by dx equal to x plus 2y plus h plus 2k minus 3 divided by 2x plus y plus 2h plus k minus 3. Now, we will have to find h and k in such a way that h plus 2k minus 3 is equal to 0 and 2h plus k minus 3 equal to 0. On solving these two linear equations in h and k, we obtain h equal to 1 and k equal to 1. And so, the equation now reduces to dy by dx equal to x plus 2y over 2x plus y. Now, let us put y equal to vx, and then we shall have v plus x dv over dx equal to 1 plus 2b over 2 plus b. Now, we can separate the variables x and b and then integrate. We shall have integral 2 plus b dv over 1 minus v square equal to integral of dx over x plus c, which will be equal to log x plus c. In the left hand side, we break it into partial fractions. The partial fractions are 3 by 2 into 1 over 1 minus b plus 1 over 2 into 1 over 1 plus b. So, after integration, the left hand side will become minus 3 by 2 log 1 minus b plus half log 1 plus b, and we get the general solution of the given differential equation after substituting the value of v, that is minus 3 by 2 log 1 minus y over x plus half log 1 plus y over x equal to log x plus c, where capital Y is equal to y minus 1 and capital X is x minus 1. So, let us put their values and get the general solution of the given differential equation. Now, let us consider the case of those differential equations where a over a dash becomes equal to b over b dash. Now, in this case, you can see that a b dash minus b a dash is equal to 0. So, the previous case cannot be applied. Let us take a over a dash equal to b over b dash equal to 1 by t. Then we will be getting dy by dx equal to ax plus by plus c over t times ax plus by plus c dash. Let us put ax plus by equal to u, then we will have, after differentiation with respect to x, a plus b dy by dx equal to du by dx, which will give us the value of dy by dx as 1 over b into du by dx minus a, and so the equation 4 will become 1 over b into du by dx minus a equal to u plus c over tu plus c dash. And then we can separate the variables u and x and use the method of separation of variables to solve this differential equation. We can put the value of u as ax plus by to obtain the general solution of the given differential equation. Let us take an example of a differential equation of this type. Consider 2x plus y plus 1 into dx plus 4x plus 2y minus 1 into dy equal to 0. You can see here that a over a dash is equal to b over b dash equal to half, and so this differential equation belongs to the case of a over a dash equal to b over b dash. We can write the given differential equation as dy by dx equal to minus 2x plus y plus 1 over 2 times 2x plus y minus 1. So, let us put 2x plus y equal to t, which will give us dt by dx minus 2 equal to minus t plus 1 over 2t minus 1, or we may say dt by dx equals 3 times t minus 1 over 2t minus 1. We can separate the variables t and x. This will give us 2t minus 1 over 3 times t minus 1 dt equal to dx. After breaking the left hand side into partial fractions, we shall have 2 over 3 plus 1 over 3 into t minus 1 dt equal to dx. And when we integrate both sides of this equation, we shall have 2 over 3 into t plus 1 by 3 log t minus 1 equal to x plus c. On substituting the value of t, we shall have 2 over 3 into 2x plus y plus 1 over 3 log 2x plus y minus 1 equal to x plus c, or we will have x plus 2y plus log 2x plus y minus 1 equal to c dash, where c dash is a new arbitrary constant and is equal to 3c. Now, let us consider the case of exact differential equations. A first order differential equation Mdx plus Ndy equal to 0 is said to be exact if the left hand side of the differential equation, that is Mdx plus Ndy, is the total or exact differential of some function of x and y, say u x y. That is to say that du is equal to Mdx plus Ndy equal to 0, and if this is the case, then we can write the general solution of the given differential equation as uxy equal to c after integration. Now, we have an important theorem here which gives us necessary and sufficient condition for the differential equation Mdx plus Ndy equal to 0 to be exact. The theorem is the following: if mxy and nxy have continuous first partial derivatives in a region R of the xy plane whose boundary is a simple closed curve, then the necessary and sufficient condition for the differential equation Mdx plus Ndy equal to 0 to be exact is delta m over delta y is equal to delta n over delta x. Now, a simple closed curve is a closed curve which does not intersect itself. For example, you can take a circle, or you can take an ellipse, or you can take a square, or you may take a rectangle, but if you take the number 8, it is a closed curve, but since it intersects itself, it cannot be called as a simple closed curve. So, let us prove this result. First, we show that the condition is necessary, that is, we shall assume that Mdx plus Ndy equal to 0 is an exact differential equation, and then we shall show that the first order partial derivatives of m and n, that is delta m over delta y and delta n over delta x, are equal to each other. So, let us assume that Mdx plus Ndy is an exact differential equation. Then we may write Mdx plus Ndy equal to du for some function u of x and y. Since u is a function of x and y, we shall have the differential du is equal to delta u by delta x into dx plus delta u by delta y into dy, and on comparing it with Mdx plus Ndy, we shall then have m equal to delta u by delta x and n equal to delta u over delta y, which will give us delta m over delta y equal to delta square u over delta y delta x, and delta n over delta x equal to delta square u over delta x delta y. Now, since we have assumed that the first order partial derivatives of m and n are continuous, the second order partial derivatives of u, delta square u over delta y delta x and delta square u over delta x delta y are continuous and are therefore equal. So, this will give us delta m over delta y equal to delta n over delta x, which is the necessary condition for exactness. Now, let us show that the condition is sufficient. So, let us assume that delta m over delta y is equal to delta n over delta x. Further, we assume that integral of m with respect to x is say u, where while integrating we assume y as a constant. This will give us m equal to delta u over delta x on differentiating partially with respect to m x on both sides. So, this will imply that delta m over delta y is equal to delta square u over delta y delta x, or delta n over delta x equal to delta square u over delta x delta y, since delta m over delta y and delta n over delta x are equal and the first order partial derivatives are continuous. Then we shall have delta over delta x of delta u over delta y equal to delta n over delta x, implying that n is equal to delta u over delta y plus f y. On integrating with respect to x, keeping y as a constant. So, here the constant of integration in general will be a function of y, which we have denoted by fy, and this will give us Mdx plus Ndy equal to delta u over delta x into dx plus delta u over delta y plus fy multiplied by dy. Now, delta u over delta x dx plus delta u over delta y dy can be written as du, and we have du plus fy dy as the right hand side, which is equal to differential of u plus integral fy dy, and thus we have shown that Mdx plus Ndy is the exact differential of some function u plus integral fy dy, and hence Mdx plus Ndy is an exact differential equation. So, this is the proof of the theorem. Thus, if the equation Mdx plus Ndy equal to 0 satisfies delta m over delta y equal to delta n over delta x, then the equation is exact, and in order to solve such an equation, let us note that Mdx plus Ndy equal to 0 becomes the differential of u plus integral fy dy equal to 0, which implies that u plus integral fy dy equal to c. That is, the general solution of the exact equation Mdx plus Ndy equal to 0 is nothing but integral Mdx, which is u, plus integral fy is the terms of n which do not contain x, into dy equal to c. So, while finding the solution of the given differential equation Mdx plus Ndy equal to 0, we shall simply have to find the integral of m with respect to x and the integral of those terms of n which do not contain x, and then take the sum of the two and put it equal to c, which is an arbitrary constant. Now, let us take an example of an equation of this type: 2xy plus y minus 10y into dx plus x square minus x tan square y plus sec square y into dy equal to 0. So, here m is equal to 2xy plus y minus 10y, and n is equal to x square minus x tan square y plus sec square y. When we find the partial order derivatives of m and n with respect to y and x, we shall have delta m over delta y equal to 2x minus 10 square y, and delta n over delta x equal to 2x minus 10 square y. So, they are both equal, and therefore, the given equation is an exact differential equation, and hence the general solution of the differential equation will be integral of m, that is integral of 2xy plus y minus 10y dx plus integral of those terms of n which do not contain x, that is integral of sec square y dy equal to c. In the first integral, we integrate with respect to x, keeping y as a constant, which will give us x square y plus xy minus x tan y, and then the second integral sec square y dy gives us tan y. So, we get the general solution as x square y plus xy minus x tan y plus tan y equal to c. Let us take one more example of an exact differential equation: y square into e to the power xy square plus 4x cube into dx plus 2xy into e to the power xy square minus 3y square into dy equal to 0. So, here you can see that delta m over delta y is equal to 2y into e to the power xy square plus 2xy cube into e to the power xy square. We have differentiated m partially with respect to y, keeping x as a constant, and when we differentiate n with respect to x, keeping y as a constant, that is, we find delta n over delta x, we get 2y e to the power xy square plus 2xy cube e to the power xy square. So, delta m over delta y and delta n over delta x are both equal, and therefore, the given equation is an exact differential equation. Hence, the solution of the differential equation is integral m dx, where y is constant, plus integral of terms of n not containing x dy equal to c, which will give us integral of y square e to the power xy square plus 4x cube dx, where we will take y as a constant during integration process, and then integral of minus 3y square dy equal to c, and we can see that the integral is e to the power xy square plus x4 minus y cube equal to c, which is the required solution. Now we shall consider equations that are reducible to exact form. Sometimes the differential equation which is not exact can be made so on multiplication by a suitable function of x and y. We call this function as an integrating factor. In several cases, after regrouping the terms of the differential equation and recognizing each group as being part of an exact differential, the integrating factor can be found. The following integral combinations may be used for this purpose. X dy plus by dx is differential of xy, x dy minus by dx over x square is the differential of y over x, and x dy minus by dx over y square is equal to minus d of x over y. X dy minus by dx over x square plus y square is the differential of tan inverse y over x, and x dy minus by dx over xy is the differential of log y over x, and so on. Now let us consider the differential equation y dx plus log x dx minus x dy equal to 0. We may write the given ordinary differential equation as y dx minus x dy plus log x dx equal to 0. We can regroup the terms y dx and minus x dy together and write y dx minus x dy plus log x dx equal to 0. Now let us divide the differential equation by x square. If we divide it by x square, we can note that y dx minus x dy over x square is an exact differential of a function of xy, and log x over x square is integrable with respect to x. So by dividing this differential equation by x square, it becomes an exact differential equation, and we note that the first term is equal to minus d of y over x plus log x over x square dx equal to 0. Now we can integrate with this both sides, and we have minus y over x plus integral of log x over x square dx. Log x over x square can be integrated by parts. We will have the solution as minus y over x plus log x into minus 1 over x. Here we are taking log x as the first function and 1 over x square as the second function. So we have the first function log x, the integral of the second function 1 over x square as minus 1 by x, minus integral of the derivative of log x, that is 1 over x, into the integral of 1 over x square, which is minus 1 over x, and then we shall, after simplification, we shall have the solution as minus y over x minus log x over x minus 1 over x equal to c, which can be written as y plus cx plus log x plus 1 equal to 0, which gives us the general solution of the given differential equation. Next, let us consider the case of the differential equation x square y minus 2xy square dx minus x cube minus 3x square y dy equal to 0. We regroup the terms here again and write it as x square into y dx minus x dy plus 3x square y dy minus 2xy square dx equal to 0. We note that since d of x over y is equal to y dx minus x dy over y square, we divide this equation as by x square y square, then the first term will become y dx minus x dy over y square, which will be differential of x over y, and the second term and the third terms 3x square y dy minus 2xy square dx will be turned into 3x square y dy minus 2xy square dx over x square y square. Now let us note that the numerator of the second term in the left hand side of the above equation is same as the numerator of 1 over y into differential of y cube over x square. What we do is we rewrite the given differential, the above equation as differential of x over y plus x square into 3y square dy minus y cube into 2x dx over x square y cube equal to 0, and then we multiply by x square in the numerator and denominator, we shall have d of x over y plus x square over y cube into x square into 3y square dy minus y cube into 2x dx over x to the power 4 equal to 0, which will give us differential of x over y plus differential of log 2 over x square equal to 0. And so we can now obtain the solution of the given differential equation easily as x over y plus log of y cube over x square equal to c, which is the required solution. Now let us find the integrating factor for a homogeneous equation. Let us recall that a homogeneous equation is one where dy by dx is equal to a function of y over x. So if Mdx plus Ndy equal to 0 is a homogeneous equation of x and y, then it follows that 1 over mx plus ny is an integrating factor. That is, we multiply the equation Mdx plus Ndy equal to 0 by 1 over mx plus ny, provided mx plus ny is not equal to 0, it will become an exact differential equation and we can easily find its solution. So let us look at the differential equation x square y minus 2xy square dx minus x cube minus 3x square y dy equal to 0. You can see here that dy over dx is equal to a function of y over x, and so it is a homogeneous equation. We can solve this differential equation by the method of homogeneous equations also, where we put y equal to b into x. Here we shall find the integrating factor, an integrating factor for this differential equation, that is 1 over mx plus ny, and then we will multiply this differential equation by 1 over mx plus ny and make it an exact differential equation, and from there we shall find the general solution of this differential equation. So let us see this equation. For this equation, the integrating factor 1 over mx plus ny comes out to be 1 over x square plus y square. So obviously mx plus ny is not equal to 0, and therefore multiplying the given differential equation throughout y, 1 over x square y square, we shall have 1 over y minus 2 over x dx minus x over y square minus 3 over y dy equal to 0. Now we shall group the terms 1 over y dx with minus x over y square, that will be differential of x over y, and the integral of minus 2 over x will give us minus 2 log x, the integral of 3 over y will give us 3 log y, and so we will get the general solution as x over y minus 2 log x plus 3 log y equal to c. Let us take one more example of a homogeneous equation, x square y dx minus x cube plus y cube dy equal to 0. So in this case 1 over mx plus ny is equal to minus y to the power minus 4. Multiplying the given equation by the integrating factor, it will transform into minus x square over y cube dx plus x cube plus y cube over y to the power 4 dy equal to 0, which is an exact differential equation, and therefore the general solution is, so we will integrate m with respect to x, assuming y as a constant, that will give us minus x cube over 3y cube, and then we integrate those terms of n which do not contain x with respect to y, that will give us log y, and we shall have minus x cube over 3y cube plus log y equal to log c, or we shall have y equal to c into e to the power x cube over 3y cube as the general solution of the given differential equation, where c is an arbitrary constant. Now we take up the case of those ordinary differential equations which are of the type f1 xy into y dx plus f2 xy into x dy equal to 0. f1 xy is a function of xy, f2 xy is also a function of xy. So the differential equation, in the case of such differential equation, we shall see that an integrating factor is 1 over mx minus ny. That is, when we multiply this equation by 1 over mx minus ny, it will become an exact differential equation. So let us consider the case of the differential equation x square y square plus xy plus 1 into y dx plus x square y square minus xy plus 1 into x dy equal to 0. X square plus y square plus xy plus 1 is a function of xy, which we can regard as f1 xy into y dx, plus x square y square minus xy plus 1 is another function of xy, which we may regard as f2 xy into x dy equal to 0. So, this differential equation we can solve using the integrating factor 1 over mx minus ny, and the integrating factor when we find 1 over mx minus ny comes out to be 1 over 2x square y square. So, let us multiply the given equation by this integrating factor, and we shall have 1 over 2y plus 1 over x plus 1 over x square y dx plus 1 over 2x minus 1 over y plus 1 over xy square dy equal to 0. So, here m is equal to half y plus 1 by x plus 1 by x square y, and n is half x minus 1 over y plus 1 over xy square. Now, this differential equation is an exact differential equation. So, to find the general solution of this, we just integrate m with respect to x, taking y as a constant. That will give us half xy plus log x minus 1 over xy, and then we add to it the integral of those terms of n which do not contain x, that is integral of minus 1 over y, which is minus log y, and put it equal to a constant. So, we shall have the integral as half xy plus log x plus log y minus 1 over xy equal to c, which is the general solution of the given differential equation. Here we can also find it by regrouping the terms and then writing them as exact differentials of some functions of x and y. So, that way also we can do. So, the general solution is half xy plus log x plus log y plus minus 1 upon xy equal to c. And then we take another example of a differential equation of this type: xy sin xy plus cos xy into y dx plus xy sin xy minus cos xy into x dy equal to 0. So, here again we have the differential equation as a function of xy into y dx plus a function of xy into x dy equal to 0, and we note that 1 over mx minus ny is equal to 1 over 2xy cos xy. So, it is an integrating factor for the given equation. Let us multiply the given equation by this integrating factor. The equation becomes tan xy into y dx plus x dy plus dx over x minus dy over y equal to 0, and which will give us now y dx plus x dy is the exact differential of xy. So, this is tan x, left first term can be written as tan xy into differential of xy, and therefore, when we integrate it, we will get log of sec xy. Integral of dx over x will give us log x, integral of dy over y will give us log y. So, we will get the general solution as log sec xy plus log x minus log y equal to log c, which after simplification we can write as x sec xy equal to cy. This gives us the general solution of the differential equation. Now, let us consider the case of those differential equations Mdx plus Ndy equal to 0, where when we find 1 over m into delta n over delta x minus delta over m over delta y, and it turns out to be a function of y only, then exponential of integral of fy dy is an integrating factor for Mdx plus Ndy equal to 0. For example, let us consider the differential equation xy cube plus y dx plus 2 times x square y square plus x plus y 4 dy equal to 0. So, here m is xy cube plus y, and n is 2 times x square y square plus x plus y 4 equal to 0. And when we find 1 over m into delta n by delta x minus delta m over delta y, we shall have 4xy square plus 2 minus 3xy square plus 1 over y times xy square plus 1, which after simplification gives us 1 over y, and therefore the integrating factor is e to the power integral of 1 over y dy, which is equal to e to the power log y, and e to the power log y is y. So we multiply the equation by y throughout and have x y4 plus y square dx plus 2x square y cube plus 2xy plus 2y5 dy equal to 0. Now this is an exact differential equation, and so the general solution will be integral of m with respect to x taking y as a constant, that is x square by 2 into y4 plus xy square plus integral of those terms of n which do not contain x, that is integral of 2y to the power 5 with respect to y, which will give us 2 times y to the power 6 over 6 equal to c, and hence we have half x square y4 plus xy square plus y to the power 6 over 3 equal to c, which is the general solution of the given differential equation. Let us take one more example of a differential equation of this type. Let us solve 3x square y to the power 4 plus 2xy into dx plus 2x cube y cube minus x square dy equal to 0. Here we find 1 over m delta n over delta x minus delta m over delta y equal to minus 2 over y, and therefore integrating factor is e to the power minus integral of 2 over y dy, which is equal to e to the power minus 2 log y, or we can say e to the power log y to the power minus 2, which is equal to 1 over y square. So let us multiply the given differential equation by 1 over y square. We shall have 3x square y square plus 2x over y dx plus 2x cube y minus x square over y square dy equal to 0. We will integrate m with respect to x, that will give us x cube y square, and then we will have x square over y. Now we will take only those terms of n which do not contain x, and we can see here that in n both the terms contain x, so the contribution from n will be 0, and therefore we have the general solution of the differential equation as x cube y square plus x square over y equal to c, where c is an arbitrary constant. Now if an ordinary differential equation is of the type where 1 over n into delta m over delta y minus delta n over delta x comes out to be a function of x only, then the exponential of integral fx dx is an integrating factor for the differential equation mdx plus ndy equal to 0. So let us take an example of a differential equation of this type. Let us consider 3xy minus 2ay square dx plus x square minus 2axy dy equal to 0. So here we will find 1 over n into delta m over delta y minus delta n over delta x. This will be equal to 3x minus 4ay minus 2x minus 2ay over x square minus 2xy, which is equal to 1 over x, and hence it is a function of x only. So e to the power integral 1 over x dx, which is e to the power log x, and e to the power log x is equal to x, is an integrating factor for the given ordinary differential equation. Hence multiplying the given ordinary differential equation by x throughout, we shall have 3xy minus 2ay square into x dx plus x cube minus 2ax square y into dy equal to 0. Now here m is equal to 3x square y minus 2axy square. So when we integrate it with respect to x, keeping y as a constant, we shall have x cube y minus ax square y square, and in n both the terms contain x, so the contribution from n will be 0, and therefore we shall have the solution of the given differential equation as x cube y minus ax square y square equal to c. Now we consider the equation mdx plus ndy equal to 0, which is of the type x to the power a into y to the power b into m by dx plus nx dy plus x to the power a dash into y to the power b dash into m dash by dx plus n dash x dy equal to 0. An integrating factor for such a differential equation is x to the power h into y to the power k, where a plus h plus 1 is equal to b plus k plus 1 over n, and a dash plus h plus 1 over m dash is equal to b dash plus k plus 1 over n dash. Let us take up an example of a differential equation of this type. Let us consider y square plus 2x square y dx plus 2x cube minus xy dy equal to 0. This differential equation may be written as y into y dx minus x dy plus x square into 2y dx plus 2x dy equal to 0. And when we compare it with the standard form of a differential equation of this type, we find that here a is equal to 0, b is equal to 1, m is equal to 1, n is equal to minus 1, a dash is equal to 2, b dash is 0, m dash is equal to 2, and n dash equal to 2. And therefore, integrating factor is x to the power h into y to the power k, where h and k satisfy the two equations a plus h plus 1 over m equal to b plus k plus 1 over n, which gives us h plus 1 equal to minus k minus 2, and a dash plus h plus 1 over m dash equal to b dash plus k plus 1 over n dash gives us the other equation involving h and k as h plus 3 equal to k plus 1. When we solve these two equations, we have the values of h and k as minus 5 by 2 and minus half. So, let us multiply the equation, given equation by x to the power minus 5 by 2 into y to the power minus half throughout. We shall have x to the power minus 5 by 2 y to the power 3 by 2 dx minus x to the power minus 3 by 2 into y to the power half dy plus 2x to the power minus half into y to the power half dx plus 2x to the power half y to the power minus half dy equal to 0, which is an exact differential of minus 2 over 3 x to the power minus 3 by 2 into y to the power 3 by 2 plus an exact differential of 4x to the power half y to the power half equal to 0. On integration both sides, we have the general solution of the given differential equation as minus 2 by 3 x to the power minus 3 by 2 into y to the power 3 by 2 plus 4 x to the power half y to the power half equal to c. In our lecture today, we have covered the cases of all those differential equations of first order and first degree where the variables can be separated, the homogeneous equations and the exact equations, and also those differential equations which can be reduced to any one of those three forms. In our next lecture, we shall consider the case of linear ordinary differential equations of first order and first degree, and also those differential equations of first order and first degree which can be reduced to the linear form. We shall also consider the orthogonal trajectories. Thank you.